Alright, well hello river lovers. Today we're going to do a presentation called Developing SQT Reference Curves. And this presentation is primarily for SQT managers or SQT developers, people who are putting together an SQT and you've gotten to the part of the process where you need to develop reference curves. And there really is an art and science to doing that, so we're going to walk you through the process and give you some examples from a bunch of different SQTs to hopefully help make the process a little bit easier. All right, so there are a lot of terms that go into this. I'm just going to go over a few key terms to help us with the actual part of developing reference curves. So we're going to go over functional capacity. We're going to talk about reference standards and thresholds, this idea of what reference condition is. And I just want to acknowledge up front that there's been a lot of effort to align these reference curve development processes with the federal mitigation rule and supporting documents. So I'm going to point you to 3 supporting documents that you might want to read or look over to help with the overall process of an SQT regionalization and in part the reference curve component. So the SQT itself is based off of the stream functions pyramid framework, which is described in this document, a function-based framework for stream assessment and restoration processes. And then ERDIC developed this guidebook to help the regulatory program, help core districts and others who are putting together function-based stream assessments that they can use in the regulatory program. It includes a regionalization process. The SQT, for the most part, follows this process as well. And then the last document is this stream mitigation accounting metrics. And it's kind of a sister document to the ERDIC document. The ERDIC document focuses on the stream assessment method, and then this stream mitigation accounting metrics gives units back to the assessment within the regulatory program so that you can have debits and credits in units of feet, or functional feet is what the SQT uses, but it also evaluates area and volume to a degree, but mostly feet or length and area. All right, so let's talk about functional capacity. This one's really important to understand for developing reference curves. And functional capacity it comes from the federal mitigation rule, and it's the degree to which an aquatic resource performs a specific function. So we have put these things into 3 buckets. The functioning at risk, not functioning is sort of our way of determining what this degree of function will be. It's not unique to the SQT. Other assessment methods use this as well. In the framework, so the stream functions pyramid framework level, these are just categorical. And then the SQT goes a step further and puts a scale of 0 to 1 on top of these categories. So we'll lay that out as we move through the process. I'm not going to do too much reading as we go through this presentation, but I will read a bit here. So this is in most of the science support documents for the SQTs. And again, it takes functional capacity, puts them into these 3 buckets of functioning, functioning at risk, and not functioning. And then you can see the index score range going with these categories. So functioning ranges from 0.7 to 1, functioning at risk 0.3 to 0.69, and then not functioning 0 to 0.29. So the definition for functioning says a functioning value means that the metric is quantifying or describing the functional capacity of one aspect of a function-based parameter in a way that supports aquatic ecosystem structure and function. So there's a few things to unpack there. One is, recall that with the SQT we have the functional categories from hydrology up through biology, and then within those categories we have function-based parameters that describe the functional statement in that category, and then the metrics are attached to the parameters. So this functional capacity score, reference curves, take place at the metric level. And when we say something is functioning, we mean that it is supporting, that metric is supporting one aspect of the overall parameter in a way that would support an aquatic ecosystem structure and function. And we pulled a lot of this from the reference standard concept that defines reference condition for biological integrity by Stoddard et al. In 2006. So this is important as well. The score of 1.0 represents an unaltered or pristine condition, native or natural condition, and that range of 0.7 to 1 accounts for the natural variability from an undisturbed to least disturbed condition within the reference condition. So it acknowledges that you might have natural floods, natural fires, other natural things that happen in, say, a wilderness system, and so those functions would vary, but they're still considered functioning. And now let's go down, so we'll skip functioning at risk for a minute, go to not functioning. So here, a not functioning value means that the metric is quantifying or describing one aspect of a function-based parameter in a way that does not support aquatic ecosystem structure and function. So an index value less than 0.3 represents an impaired or severely altered condition relative to reference standard. And an index value of 0 represents a condition that provides no functional capacity for that metric. So when I'm thinking about this, I like to think about the 0 and the 1. The 0, no function for that particular metric, no functional capacity. The 1.0, full function or a pristine function. And I know if you're listening to this, you're like, but we don't know what pristine is anymore. And just hang on, I'll get to that. We will definitely address that. All right, so reference standard, just kind of as a reminder, we put them into these three buckets categorically of functioning, functioning at risk, not functioning. It's linked to the metrics, and it's based on this idea of reference condition, reference standard. So for the SQT, for these reference curves, reference condition is a set of quantifiable characteristics of the ecosystem that characterize the range of natural variability under undisturbed conditions. So just sort of reframing what we already said about that 0.7 to 1.0. It is culturally unaltered or pristine. It is not the best attainable. And again, I'm going to get into a little bit more detail on that a bit later, but we have to be very careful when we're going out and collecting data for the purpose of developing reference curves to not just say we're finding the best sites we can find in our region, in our state, and that will be referenced kind of blindly without going through another level of peer review from our technical teams to say, but is that really reference condition? This is the heart of developing reference curves. This is the crux of developing reference curves. This is where we'll spend the most time in this presentation. Again, just kind of setting up the language and the definitions for now. So the reason this is important, why is it important to set the 1.0 at pristine? And it's because best attainable often does not equal reference condition definition. So we often are working with states and we want to go out and collect data. Maybe there's some funding to go out and collect data. So we need sites, right? And so that site selection criteria, the goal is to get reference, but then the site selection criteria often requires public land, easy access, near roads. And so we don't just say we're going to wilderness sites. And even if we said that, some states have very few, if any, wilderness sites left. And so this idea of reference immediately gets watered down based on just the reality of life. We need permission to access a site, so that's why public land is often selected, and then easy access to roads because we've got budgets and schedules and we're trying to do these things quickly. And I'm not saying that is wrong, but I'm saying it often will lead to that site really not being true reference condition. It's also and I'm gonna as we move through here, I'm gonna kind of walk you through how we go about fending this off. Like, we know that this is a problem across assessment methods, that people call it reference, but but they're limited to just finding the best they can, and they think data drives everything. Data is important, so whatever the data is for that site is what they're going to set as reference. And I'm recommending that that's not the case, that that's the starting point, but then there's a decision of experts who may adjust those values. All right, the second point is that it is counter to what the tool is trying to do with functional uplift. It's always important to remember that the SQT and these reference curves are going to be measuring a before and after value, and we're focused on the change. And so keeping in mind that the 0 being no function and the 1.0 being pristine function gives you that full range of functional capacity, so that when you do a project, wherever you are on that scale, you can measure the change. Some projects do start with really bad streams, and they create very good streams, not pristine streams. We're not going to have 1.0s across the board from our scoring, but when we have the full scale represented, we can see we have better confidence that we're going to capture that change. And then the third point is that if we don't do this, we can run into examples where it just doesn't pass a reality check in practice. And we've seen this happen with teams who have gone about putting reference curves together. There was one state, I won't call them out, where they were just really adamant that no, whatever site we say is reference, that will be reference. We acknowledge that it's just the best site we could find. We acknowledge that the forest is only 30 years old, but we've got to call it reference. And that really plays out with a wood score. So large woody debris is a great example when your best attainable site is a young forest. A young forest is just not going to produce very much wood. And if that stream was channelized at some point in the past or cleaned out of wood, it will not have much wood. And that was the case in this state, but they built their reference curves off of it. Fast forward to implementing the SQT, and they all go out to this site. They're doing an existing condition assessment on a stream going through a pasture. There was one tree in this pasture that had dumped about 3 pieces of wood into the channel, and it scored reference. It was between a 0.7 and a 1. And every single person who's standing on the bank looking at this reach is like, there's no way that this is reference condition for wood. So that's what can happen if we don't bring in sort of the critical thinking and the decision making to accompany the data collection. All right, so the one point I really want to drive home with this is that reference curve development is a process. So we start with that team of experts. We select our parameters and our metrics. We think through, will there be stratification? Then we develop the reference curves. Then we test and define. So I'm going to go through these steps, but I'm going to focus on developing the reference curves. So we start with our team of experts. You really want a team of professionals who have the academic background and practical training in each assessment method / parameter / metric, and work together to develop the reference curve. So, example experts, you want your fluvial geomorphologists, your hydrologists and engineers, your plant biologist, your aquatic ecologist, water quality scientist. These people don't need to be on every single technical team. Typically we take these teams and create them by either functional categories, so like people who are experts in hydrology or people who are experts in biology, to deal with the parameters and metrics within those categories. But it is good, especially when we get into certain metrics, to have a range of expertise. But you want to have the people who are experts in that assessment method who are making these decisions. All right, I'm not going to spend that much time on the parameter and metric selection for this presentation because we're just focused on the reference curves. But just note that that is part of the process. The team selects the parameters and metrics to include in the SQT. As I noted, generally that's by functional capacity. And then I'll just note as we move forward that some metrics are easier to develop reference curves for than others. So there are some curves where you don't need data for setting the no functioning or the 0.0 threshold. So I'll show you some examples of that. But I would argue that all of the curves need data for setting that 1.0 threshold. Another part of the process that's important is determining if a reference curve needs to be stratified. So stratification is here to account for the natural variability among stream systems. Reference curves for specific metrics may be stratified by differences in stream type, ecoregion, etc. So think about this as, we develop SQTs typically at a state level. So, I'm here in North Carolina. If we have a North Carolina SQT, well, we also have the mountains, the Piedmont, and the coastal plain. And we know that macroinvertebrate communities, fish communities, riparian vegetation vary by those physiographic regions. So physiographic region could be a stratification so that when we assess fish, for example, we assess it, we have separate reference curves for mountains, Piedmont's, coast. If we have better data, we could refine that stratification to ecoregion or even watershed. So you can determine as your team of, again, this is where the experts come in, like what level of stratification, if any, does that metric need? So some metrics do need stratification, other metrics do not. All right, so now we'll get into the what I call the anatomy of a reference curve. So we're just going to kind of walk through this reference curve, and we'll start on the x-axis. The SQTs label the x-axis as a field value, and then the units can be whatever. This example was a ratio. It could be in feet, could be in meters, it could be anything really. I think if I had it to do over again, I would not call this field value. I would just call it the metric assessment result. That's a little more accurate. We do have some metrics that are desktop. They're not all collected in the field. So in terms of just thinking about what's this x-axis, it is however you are assessing that metric, it's that result. So you could think of riparian vegetation as a function-based parameter. Riparian width is an example of a metric under that parameter. So the riparian width, maybe in feet, would be what you're plotting on the x-axis. If it was composition, it might be, a percent of shrubs, for example, as your metric. Whatever that metric assessment output is, in whatever unit it is. And then the y-axis is your index value. This is always the same across every metric, ranging from 0 to 1.0. This is our functional capacity. You can see those categories are superimposed on here. The not functioning, the functioning at risk, the functioning, those thresholds between the categories at 0.3 and 0.7. And then we have our 0 being no function and our 1.0 being pristine function. And then that 0.7 to 1 being the reference standard or reference condition range. And as I'm sort of making the pitch, I feel like this is the most important range of data or decision making to be made. What is reference? It's the hardest to do. And then we have threshold values. So I'm going to use this term a lot as we move forward. What are the threshold values? In this example, there are 3 threshold values. There's the, in this example, a 1.0 in the metric assessment result yielded a 0 function. And then a, 7.4 or so represented a 1.0 or pristine function. And then the 2.2 or so was the 0.7. So there's only 3 points that are being used to develop this curve. And you can see regression equations are put to these points, but it's important to note these are not regression lines through a data set like we would normally do. We would normally have like an XY scatter plot,
and then you fit a best fit line through those points. That's not what this is doing. I mean, it is mathematically, but this is not a data set. These were decisions that the team made to create these threshold values, and then the equations are developed. The purpose of the equations are to give us that change in functional capacity per change in the metric assessment result. It is a finer, it's just a finer way to capture functional capacity change than just having categories of good, fair, poor. You know, you can't tell where you are within those categories. So that's the purpose of the equations. All right, so as I noted, the reference curve development, it is a process. We're going to start with either data or some kind of rationale. So we have our data gathering, data collection, and then we're going to move into, we've got to set those thresholds, and then from the thresholds, we can create the curves. So what you're going to see as I go through this is that it starts with data or information, rationale, and moves into decision making. So we have a bit of a process we follow for making that decision making. So, and really, the decision making really is in the thresholds. Like, where are we going to set thresholds? And we get that information from either new or existing data sets, from the literature, which could be peer-reviewed, government documents, conferences, existing indices, so like water quality programs, and then best professional judgment from the technical team. So we use this if we don't have data. So sometimes that is the case. So I'm going to walk you through examples of each of these. So we'll start with new and existing data. So here's an example. So we'll start with the data. So this is the metric. ER stands for entrenchment ratio. I don't care if you know what that is or not for this. You could think of it as a form of floodplain width. In this example, it is stratified by stream type. So we have reference Cs and reference Es. We have a nice big data set for both of these. And so you can see the box plots for the C and the box plot for the E. And then this table, these are the thresholds. And so this particular technical team of geomorphologists and hydrologists said, all right, we're going to set the 1.0, this pristine value, for a C stream type. So we're working off this blue box plot at a 7.3 value. That's the 75th percentile. That is quite common, by the way. Don't have to do it, but it is pretty common that if you have a technical team, you have a data set that you know came from reference condition, setting the 1.0 as the 75th percentile is pretty common. Sometimes, actually often, people will then set the 25th percentile as the 0.7. Here it looks like that might be 2.5 or 3. This particular team said we're going to set the 0.7 at a 2.2, which is the Roskin classification value. And so anything below that would begin to change the stream type and kind of impair functionality, was their logic. And then they set the 1.0 at a 0, meaning the floodplain width is equal to the channel width, therefore there is no floodplain and there is no function. So the point I want to try to make as we go through these is not so much to sell you on their result, but to describe the process that these teams went through, so that if you're getting ready to do this, you can have a better understanding of the thought process. You may come up with different answers, which is fine, but we do recommend you follow this process. All right, here's another example of collecting data. So this is for a particular watershed. So the Moose Creek watershed, this is in Alaska, and the forest here is about 80 years old, and they did wood assessments using a method called the Large Woody Debris Index, and they did it for pretty much the whole watershed, and they plotted their LWDI scores for the whole watershed,
and then began to develop their reference curve. So I'm going to start with the 0. So they said 0 wood equals 0 functional capacity. So that's pretty easy. And then they said, all right, we're going to set the 0.3 at 161, which was all the way down here at the minimum number that they found. It's kind of the outlier of the low. So that's setting the 0 down here to the very low values as not functioning. And then they came up here to the 0.7, and they said 0.7 is going to be our 75th percentile. That's the 575. And then you'll see this 1500 at a 1.0. But there's no 1500 on this graph. So even the highest score they got was just over 900. So where did they come up with the 1500 and why? Let's do the why first. The why is that this watershed was logged and had a railroad going up it during when there was a coal mine to produce coal for around World War II. And so the watershed was heavily impacted then, but then once mining was done, it was kind of left alone. A nice forest has come back, very mature trees, and it is putting wood in the channel. But they were like, 80 years is thereabouts. Is that really enough to be producing reference curve, reference standard wood? And the goal of this particular project was to restore salmon habitat. And so wood was really important. They wanted to make sure that if they err, they would err on the side of having too much wood as the pristine condition rather than not enough wood. So they went to northern Minnesota SQT and looked at those reference curves that were in forests that had more intact forest, older forest, and they saw that for that ecoregion that was most similar to theirs, that's where that 1500 came from. So a decision, again, that team made, but that they could back it up. They had a rationale for doing so. All right, so I just wanted to show this example quickly. You won't always have box plots. Here's an example of where they had existing data. They collected some data, but then they also looked at just other data sets. These were not necessary. Some of these were in the literature, peer-reviewed literature. Some of these were just data sets that they were able to reach out and get from people. And so they had tables that looked like this, where they had average values, min values, max values, not box plots. Decision making is the same. I prefer to have box plots if I can, where you can really just say I'm going to use the 25th percentile or the 75th percentile. Here they decided, like, okay, for the 1.0, we're going to look at these maxes. They're kind of all over the place, but the team is saying we want deep pools. Deep pools are good from a functional capacity perspective and supporting a healthy ecosystem. So we don't want to, again, we want to make sure that we are, high enough. And so they set that at anything greater than 3. So anything greater than 3 would yield a 1. And then the 0.7 they set at 2, looking more at these average values. The 0 is 1 because, again, this is a ratio. So a 1 means that the pool width is equal to the riffle width, and therefore there is not a pool. I think this one and the wood are both examples of where you kind of don't need data to set the 0, because no wood equals no function, no pool equals no function. All right, so another method, so that was examples of how to develop reference curves from data. Here are examples of how to develop reference curves when you can get it from the literature. So again, this is pretty common. One of the things that the technical team will do after they make their parameter and metric list is just to go out and look at the literature and say what's available that we can use. So this is a metric called percent fines. Less than 2 millimeters means that it's basically sand. So what's the percent of sand in this reach? It is a part of a bed material parameter. And this particular group found a paper, Physical and Ecological Thresholds for Deposited Sediments in Streams and Agricultural Landscapes. So this particular curve, there was 2 curves for less than 2 millimeters and less than 6.35. This is just the less than 2. And if you look at this graph, you can see that in this paper, they were plotting EPT relative abundance as a percent versus percent fines, and they set an ecological threshold at 14.8. And so the team used this graph to create thresholds to convert, from this paper into a reference curve that could be used into the SQT. So the 1.0 was set at anything less than or equal to 5%. That's the end of the data here. So here's your 5%. The 0.7 was set at the ecological threshold of 14.8. And then the 0 was set at 32, which was the end of the data here. As I was looking over this to prepare for this presentation, I had the thought that, you could make an argument that maybe this 32 could be a 0.3 instead of a 0, and then set the 0 EPT percent as a 0 functional capacity. That would actually align a little bit better with the logic that I was sharing. But it is up to the technical team to make these decisions, and you can have discussion and pros and cons and what you're trying to achieve with your tool as you think through that. All right, here's another example. I'm going to do this one quickly. The main thing I wanted to point out here is that this is a thesis. So if you're developing these reference curves, we are seeing more and more graduate students, both at the master's and PhD level, do their research kind of in support of reference curves for SQT. So don't forget to reach out to your university contacts to see if anybody's working on these projects. In this example, they had sites. They don't have a very big sample size, right? Only 6 for degraded, 13 for reference, and then they also did restored streams as well. But in this example, the steering committee took that thesis and then set the 0 at 50%. So the 75th percentile, they basically said when we have more than 50% stream bank erosion, we're going to give that a 0 or no functional capacity for this particular metric, because so much sand, really sediment supply, is being delivered to that reach from bank erosion. And then they set the 0.7. They came over to the reference curve and set that at the median, and then the 25th percentile was the 1.0. All right, so then next is we got 2 more to do from the indices and then the professional judgment. I'll go over these pretty quick. This is very common method for when technical teams get into the physicochemical category, because there are a lot of states that have all types of biological or water quality assessments where they've developed their own index of biological integrity or some other form of indices. So this is one that was used in both Wisconsin and Minnesota. The point I want to make when you're doing your thresholds, I'm not going to go through this one in as much detail, is that often these indices have more categories than functioning at risk, and not functioning. So as a technical team, you have to look at these categories and say, how do we want to kind of redo these ranges to fit functioning at risk, not functioning. So you may say we want excellent, very good, and good to be functioning. We want fair and fairly poor to be functioning at risk, and we want poor and very poor to be not functioning. From that, you can then develop your thresholds, and from the thresholds, develop your reference curves. We often do see reference curves developed from indices like this have more breaks than some of the more simple curves that I have shown. All right, and then the last one is just curves from best professional judgment. So there are times when we really want to include a metric in an SQT, but we just can't, we don't have existing data. We don't have the scope and budget to go collect new data, and the literature doesn't give us clear answers either. So one that is commonly used that fits this category is called concentrated flow point frequency, which is a metric within the reach runoff parameter in the hydrology category. So this metric is saying Do we have pipes and ditches that is bringing runoff from, say, a road or a parking lot right into the stream channel? And we can certainly find literature that says that's not good from an ecological perspective when looking at runoff. We are bringing runoff into the channel. It would be better to have that treated in a best management practice before it gets to the channel. Plenty of literature on that. So our rationale for including the curve is robust. But we, as of yet, have not been able to find good literature that says, well, what is that density? How many pipes or ditches per 1,000 feet, for example, would be functioning at risk and not functioning? So the team just came together and thought through it, and through that thought experiment created the curve. And so really the 1.0 here is the easy one, because we know that in a pristine stream it would be 0. So 0 concentrated flow points equals the 1.0. And then the rest is a discussion and a negotiation. So at this point the team was like, well, I don't think more than 1 per 1,000 feet could you say that would be reference. You could make an argument that even the 0.7 should be 1. Again, this is kind of a discussion. And since we did not know what the 0 would be, we just created a very simple linear curve and extrapolated that down. So then when you get to about 3.3 per 1,000 feet, that's no function. And I will say, like Minnesota, for example, has improved this. They have a more robust metric now, sort of their own index method for doing this. So there is some movement to make this a little bit more complicated, but also to make it maybe better. That one, for example, will score a pipe will score differently than an open channel. So this is kind of, as all of these are, works in progress, but this is a way to be able to capture that in an SQT, again, using just professional judgment. All right, the thing I want to just end on is that sometimes the technical team will create a reference curve, but there's a it depends, and that it depends has turned into some rules that inform how that reference curve is going to get used within the SQT scoring. And I'm just going to give you 2 examples, armoring and the width to depth ratio state. So here's a percent stream bank armoring metric. This is a metric within the lateral migration parameter. So typically, not always, but typically there are multitude of metrics under lateral migration: a B high near bank stress rating, a percent erosion, and then armoring. And there's actually 2 rules that go with armoring. The one that's not shown here is just that you only assess armoring if it is present or proposed. And that's really more of a dilution and weighting issue within the scoring. But most technical teams have said, all right, what we want, here's the curve. Again, we don't have a lot of data on this one, so it's a very simple curve. No armoring is your pristine, and anything more than 30% armoring, this is looking at both banks on your reach, is 0 function. But then with a caveat, it says if the armoring is greater than 50%, then that whole parameter will go to 0. So that's the rule. And the thought is 50% would mean one entire bank is armored. And so the stream can't laterally migrate like it normally would in any sort of functional way. And so this is a rule that says after 50%, the parameter score goes to 0. Another common example is in width to depth ratio state. This one's a little bit maybe harder to wrap your head around. It's percent over expected. These are riffle width to depth ratios. This is in the hydraulics category now. It's really a flow dynamics assessment of the risk of aggradation or degradation. And so we focus on this curve really for the aggradation component. If your width depth ratio is getting larger and larger and larger over what it should be, then your risk of aggradation is going up. You can have a too low of a width depth ratio as well, but you're only going to use the blue portion of the curve when the bank height ratio is greater than 1.2. This would indicate incision. So if you have a stream where the width to depth ratio is going down and the bank height ratio is going up, it's incising. So this would be the incising part of the curve. This would be the aggradation part of the curve. But a width to depth ratio that's getting low but maintaining a 1.0 bank height ratio is typically just moving towards a better functional capacity. So that's the purpose of that rule. Okay, and then once you develop these curves, you're not done. You then have to incorporate them into your SQT scoring. Think about weighting. Think about how you're going to do your roll-up scoring. Then you got to go out and test them. You want to document all of those thought processes. So everything we talked about all those decision making. You want to capture those thoughts in some form of document. We typically call those our science support documents. Then you're going to go out and use the tool. You're going to learn, and you might circle back once a year or so and refine those curves based on what you've learned. All right, so if you want to take a deeper dive, I do recommend you read the science support documents. The latest one is the combined Minnesota and Wisconsin stream quantification tool science support document. So again, it does what we've been talking about. Not all, but a lot of the examples from this presentation came from that. So you can go back and kind of read through how technical teams went through their process to develop those reference curves. And I hope this helped. And it is a fun process, so get your team together, and if you follow this process, you'll be able to get your reference curves developed. All right, thank you very much.